Now that we've had a preliminary look at area underneath a curve, we're going to describe how this relates to a part of calculus known as the definite integral. So just as a quick recap of what we did in the previous section, suppose that we are given a closed interval from a to b with a nice generic looking function like this, y equals f of x. And in the previous section, we said we're interested in finding the area under this curve. Now the way that we did so is we said break this into n subintervals. And the length of those subintervals is going to be delta x, and that is b minus a over n. Then we're going to select a representative point. From each subinterval. And we're going to refer to that point as x sub I star. Now, in the previous section, this could have represented the left endpoint, could have represented the right endpoint. Ultimately, though, it didn't matter which endpoint it wound up being. Then we plug representative point into the function, which gave us f of x sub I star. Now we turn that into the height of a representative rectangle. And so the area of that representative rectangle is going to be f of x sub I star, that was the height, times the length of the base. Then what we did is we added all of those up, got a left-hand approximation, a right-hand approximation, or a midpoint approximation, and then we added all of those areas up. So then the total area under the curve was approximately equal to, this is where we're going to introduce that summation notation that we introduced right at the end of the previous section and the beginning of this section. So this represents, add up all of those rectangles like so. Now we then said for the best approximations, use a large value of n. So if we were interested in finding the exact area, we could simply take the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star times delta x. Bernard Riemann is the guy who put this together, and as a result, this summation is named for him. This is referred to as a Riemann sum. Now the notation that gets used for this in integral calculus is known as the definite integral of a function. So this is called the definite integral. And over the course of the next couple sections, we're going to talk about how to evaluate a definite integral. This symbol that you see right here that looks kind of like an elongated S is known as a definite integral symbol. A and B that are here are referring to the same A and B that we referred to back up here. They are known as the bounds of the definite integral. F of x is known as the integrand. So this is your integral symbol. A is known as the lower bound. B is known as the upper bound. And this guy right here is referred to as your integrand. Now there are a number of different ways to evaluate definite integrals. The first way is going to be to set it up as this Riemann sum and to evaluate the Riemann sum. Should probably specify definite integrals. Evaluating definite integrals. So one way is to set up the Riemann sum. That's not how you spell up. My goodness. Set up the Riemann sum. Now, setting up the Riemann sum is to say, let's take the definite integral from a to b of f of x times dx, and we'll set this up as the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star times delta x. Now you'll notice that the structure of these two statements is sort of similar. The integral sign is meant to represent an s, and the capital sigma represents an s as well. Then you've got your actual function with an x value plugged in. And you've got your delta x versus a dx. Delta x is a finite change in x, whereas dx is referring to an infinitesimal change in x. If you'll recall, the definition of delta x was b minus a over n. As it happens, when n goes out to infinity, the length of the interval is going to tend towards 0. Anything that tends towards 0 in length is referred to as an infinitesimal distance. So dx is infinitesimal? I'm not sure I spelled that right. I'm so used to saying it, I don't know if I spelled it right. That's okay though. So, setting up a Riemann sum is going to be a 6-step process. And I realize I've already used the index 1 over here, but I'm going to go ahead and reuse it. So first thing you'll do is calculate delta x. Thankfully, we have a formula for that, and that is b minus a all over n. Then, we're going to find x sub I. Now, technically, you are allowed to use any point within these intervals. What I'm going to do is go with the left endpoint. So, left endpoint for each interval means that x naught will be a, x1 will be what we get when we start at a, and then add on 1 change in x. x2 is what we get when we do a, and then add 2 delta x's. x3, that endpoint would be a plus 3 delta x's. So more generally, this can be expressed as a plus I times delta x. In order to evaluate this summation, we're going to need a function involving some i's, and this is how we get them in there. So then we're going to plug x sub I star into f. That'll give us f of a plus I times delta x, but really it's just, whatever expression you had. Then we multiply that result by delta x, which gives us f of x sub I star times delta x. This all should feel completely natural. The new stuff is going to be the following. After we've set this expression up, the next thing we'll need to do is take the summation of it. Now, in order for us to do this, that will involve some of the properties that were listed in a previous video. And finally, after you've performed your summation, the result should be a function of just n. So finally, when we take the limit as n goes to infinity, we will have our result. We'll apply this process in the next video.